Okay. Anyway, hello everyone. I'm John Readey. I've been with the HDF group for about 7 years now, and my primary focus has been on HDF as a service. So today we're going to talk about new features in HSDS, our highly scalable data service, specifically Lambda and direct access modes. So let's get started. So I'll give a brief overview of HSDS. If you need more information, there's plenty of previous talks I've given on HSDS that you can find on YouTube. And then we'll talk about AWS Lambda and then direct access. And then we're going to have a fun performance comparison with all these different modes of access. So HDF as a service. The idea is a REST-based web service for HDF data. And it was designed to be performant, good performance, and scalable. We'll talk a lot about that going forward. The idea of scalability is to be able to match the capacity of the server with the workload of the clients. Feature complete wants to support most of the features of the HDF library and support both POSIX and object storage. And it was originally supported by a NASA Access grant back in 2015. So very briefly, the architecture is like this, where you have, rather than a library, you have a set of containers that are behind a REST API. We have these blue boxes, service node containers, and they're the containers that handle client-based HTTP requests. The green boxes, the data nodes, they are the workhorses that are reading and writing to the data store. And you can kind of see here that we've partitioned the data store so that any storage object in the data store is owned by a specific data node. And then as we scale up or scale down the number of nodes, it automatically reconfigures, right? So we'll switch ownership. And the idea is that, especially in like multi-writer scenarios, you always know, who has the authority of truth of current state of any object. So as we've worked on this project, the number of platforms has expanded a lot, partly through our efforts and partly through community contributions. So we support container management platforms such as Docker and Kubernetes, Amazon EKS, Azure AKS, DCOS, and different storage systems. So originally it was S3, and then we added POSIX support and Azure Blob support. And beyond that, there are a bunch of different S3 API compatible platforms like OpenIO that can be used as well. So pros of running a service. It's nice in that the service can mediate access to a storage system. So if you have an application that is reading writing directly to the storage system, then the application needs to have authority to do that operation. But if you want to have a system where different clients have different access, then that's not feasible. When you have a service, the service can grant authority based upon permissions that are configured in the file stored in the storage system. Server can speed up things. So every time you reach into S3, for example, to grab data, there's a certain amount of latency. For frequently used data, the server can cache that data. It's much like the chunk cache or metadata cache in HDF library, except here the cache is shared among all clients accessing the service. We minimize data I/O between client and server. Okay, so for example, if I'm on my desktop, I don't need to read all the contents of all the chunks for each data access. Only the result is sent to me. Another thing, speaking of my laptop, is you could be running HSDS on a large server or cluster, and collectively provide more processing capacity than you'd have on a client-side machine. And finally, HSDS serves as a synchronization point, right? So if you have multi-reader clients that are writing to S3, S3 is not going to synchronize those updates, right? You'll end up with clients overriding each other. HSDS serves as kind of a traffic cop to make sure that all the writes are consistent. Right? It sounds great. So why not? Well, maybe I still want to bother, all the hassle of setting up a service. And then, if I have a service and even provided that I can scale that service, then you have this constant challenge, right, of scaling up the service based upon the load of the clients any given time. And finally, it costs money, right? So if I have a cluster or a large machine, that's going to add up to a significant amount of dollars over a month, say. So we're going to explore HSDS without the service aspect. And two ways of doing this, right? One is to use AWS Lambda, and two is what we call direct access model. And we'll talk about both these in detail. And the whole idea is that you provide the same capabilities as HSDS, but without the server. And so here's you can see like a little example. If I run hsinfo in this Lambda mode, I get a response. It says HSDS on AWS Lambda. Server state is ready. The endpoint, this is a API gateway, a DNS. And then username is HS Lambda. And then node count is 1 and up 2 seconds. So this whole thing came into being just as I invoked hsinfo. And we'll see how that works in the next slides. So AWS Lambda, it's a relatively new service and it's evolved quite a bit over the last few years. The price is an astounding 0.000000167 dollars per millisecond that your function runs. That sounds great, but beyond the cost savings, you have the benefit of infinite elasticity. So what I mean is that if you have no clients making requests, there's no cost. If suddenly 1,000 clients come making requests, it just automatically provides that capacity to scale up. And there's no infrastructure to do it. No server setup, no OS installations, patches, all that stuff. And clients can either invoke Lambda directly using the AWS APIs, or you can set up AWS API gateway that simulates a REST-based server. But what it does, every time a REST request comes, it gets transmuted into a Lambda call. And so we have the same REST API as with HSDS. Sounds good, but there's some challenges. One is that, unlike a server, the Lambda, everything has to be set up as fast as possible because each request is a new Lambda instance. So you don't be waiting around for the software to be ready. There's no caching, right? So if you access the same data repeatedly, you're still reading that data from S3 each time. There's a limit to the number of virtual CPUs you can have per function. And the actual runtime environment is restricted. So there's no Docker, there's no TCP, there's no shared memory. So we have to make some changes in how this is implemented. So I think I messed the slide up. So basically you have a AWS container registry that has your Docker image. Request comes in, it goes to Lambda. Lambda will set up this basically a service node and up to 3 data nodes as sub-processes rather than Docker containers. So then it sends requests to service node sends requests to data nodes talk to S3, and finally that response is returned. So it seems rather involved, and In fact, it takes around 2 seconds for even the smallest request to be serviced, which is at least 10 times longer than a typical HSDS request. But it's like an elephant riding a bike. It's not that he writes so well, it's just that they can do it. So to minimize this, we run these nodes as subprocesses, and we use main sockets versus TCP. And then, as we described, these get distributed across the service node to data nodes and getting the result. So performance constraints. So with testing, we find that the response time is maybe 2 to 100 times slower than the equivalent HSDS request, depending upon what you're doing. And it's because of the startup costs and time HSDS code needs to initialize, data being fetched from S3, and so on. So next, let's talk about direct access. So direct access is a similar idea of having serverless, but rather than invoking AWS Lambda, we run these subprocesses on the client machine itself. And so again, here's HSInfo in direct access mode. And similarly, you see that the uptime is 3 seconds, right? So when I ran HSInfo and it saw this local, H5ID set up these subprocesses that are equivalent to the data node and service nodes and made this request and got the response. So similar to Lambda, we have these service node and data nodes as subprocesses. Everything else functions just the same as with HSDS. And you can use AWS S3 or Azure Blob or POSIX Disk, et cetera. And the architecture looks like this. And performance is pretty equivalent to running HSDS on an equivalent set of hardware. So with that out of the way, let's look at some performance comparison with all these different modes of accessing HDF data. So to keep this simple, we're going to take one file. It comes from this National Renewable Energy Lab solar repository database. And the file size is 1.5 terabytes. It contains about 28 different data sets. We're going to look at one data set called wind speed that has these dimensions about 17K versus 2 million. So 66 gigabytes in this one data set. And the program will randomly choose a column from this data set and read all the data in that column. So the data set is chunked. So in reading that column, we need to process roughly 10 gigabytes of data. So the way both HSDS and HF5 library work is you can't pull out pieces of a chunk. You read the entire chunk from disk and process that. And I must say that if this is just one data point, your performance will change based upon your data and your application and your hardware, phase of the moon, et cetera. So take that for what it's worth. And so let's compare HF5 library reading from POSIX, HF5 library with the S3 VFD, HSDS on Docker, HSDS on Kubernetes, HSDS with Direct Connect, and HSDS with Lambda. The hardware for this study will have for Kubernetes, we're going to use what's called an M4 2X large. Basically, it's a 4-core machine with 32 gig RAM. For everything else, we'll use an M5 8 extra large, which has 128 gigabytes of RAM and 8 cores and 10 gigabit networking. And they're all running in the same AWS region as where the data is kept. The code you can find here. So it's one test case that can run either in library mode or with S3 VFD or with HSDS. And for HSDS, it can use direct access or Lambda or Docker or Kubernetes. And the results. So let's go over this. So with a library, it took 80 seconds, which is equivalent to a throughput of 135 megabytes per second. And I won't even dock it for the 2 hours it took to copy the file from S3 to a locally attached disk on the system. So that's pretty good. Next, if we look at the S3 VFD, it time took 328 seconds, or equivalent of 33 megabytes per second. But this has the advantage is that you don't need to provision a disk and copy the data and so on. As Elena was mentioning, this should improve greatly with recent improvements in page allocation and so on. But I wasn't able to test with that. Next, for HSDS, running on Docker with 16 nodes, we got a runtime of 16 seconds and throughput of 678 megabytes per second. So vastly superior to S3 VFD, or even just a library using locally attached disk. So I think it's really, at least in this case, it's impressive. Because so often we think of S3 as something you kind of live with, even though performance sucks, because it's cost effective and it's a global resource. But with the right kind of software, you can really extract a lot of performance out of S3. Next, we have Kubernetes with 16 nodes and 4 systems, and this was 28 seconds. So a bit slower than having one large machine, but the advantage of Kubernetes is that you can scale up to a larger cluster. And you have this flexibility to shrink or grow the cluster as your demands change. Next, Direct Connect, it's very comparable to the performance we saw in Docker. So this was, again, on the same machine, so it was able to use all those cores of the machine and got just a little bit slower performance than with HSDS. And sadly, Lambda didn't survive the test. There were some 500 errors and it wasn't able to complete, but performance wasn't looking spectacular with Lambda. Okay, so different pros and cons. I don't think there's one best solution for everything. I think it really depends upon the nature of what you're trying to accomplish. So kind of briefly, for HSDS, I'm very curious, how does it scale as you increase number of nodes on the service? And we see here, we took running the same test case again with either 1 node, 2 node, 4 nodes, 8 nodes, or 16 nodes. On this particular machine, you wouldn't want to go beyond 16 nodes because you'll be CPU constrained in your access. But we see even with 2 nodes, we're already beating the performance of HDF library. And again, this comes down to that with a library, you're reading one chunk at a time, whereas with HSDS, we can read multiple chunks simultaneously. And it just improves as you add more nodes to the system. Kubernetes performance scaled similarly with the performance of Docker. And then I won't go into detail here, but I spent some time investigating how performance scaled with the number of clients. So rather than one client, what if you have 100 clients all send requests? At some point, HSDS will say, hey, too much work, and it'll reject requests with a 503 response. You can address that by increasing the number of nodes in HSDS. And so how does that scale? How many clients can you support with a given number of nodes? And the results are here. So here it was very linear, right? So with, say, 4 nodes and 10 clients, we got 100% response rate. But if you go up to, say, 12 clients, then you start seeing some errors, and it gets worse from there. But going from 4 nodes to 8 nodes, you basically double the number of concurrent clients you can have. And the same thing going from 8 to 16, and so on.
Yeah, John, I apologize, your time is over.
Okay, sorry. Yeah, I'm just done here. Anyway, I just want to say, so next steps, want to improve Lambda performance and looking at things like streaming support, where we could kind of more smoothly handle large requests and so on. And that's it.
Okay, thank you.